Hello everyone and welcome to a new video series we are launching on the Civil Engineering Essentials channel. In this video series, we are going to be talking about nonlinear analysis using the finite element method. So this is a new series that we are launching here on the CEE channel. It's basically a continuation of the finite element method series, however, in a more advanced way, talking about nonlinear analysis. Now, of course, the question is, why would I need to understand this? We need to understand this because usually our analysis is done in the linear domain. However, our behavior of structures, especially during the failure mechanisms that we are using to design, is nonlinear. If you're, for example, designing for the ACI code or the Euro code or any usually well-known code, you would realize that you are usually dealing with a section at the ultimate phase, basically when the material is starting to crack or the steel starts to yield. This is the ultimate limit state, and it is usually done in the near failure conditions, meaning that usually our material would not behave linearly in that case, but non-linearly. We still use linear analysis, and the codes account for this, but I think that understanding nonlinear analysis is helpful academically and professionally. It's helpful academically because, nonlinear analysis is basically the general case of linear analysis, and professionally, because you could use this knowledge in order to design more economical sections by using some tips and tricks and techniques that nonlinear analysis unlocks for you, such as plastic hinges and progressive plastic hinge development, as well as momentary distribution methods. So it's kind of beneficial for both sides, especially if you are a pro or even interested in structural analysis. Nonlinear analysis is one of those topics that you should know. A small off topic I want to say here to my robot fans. I'm still struggling in implementing the wind load on the tower, and that's the reason why I am not able to publish a video thus far. I'm working on the issue and I will publish a video once it's resolved. Now, a thing I want to mention is that this video series is going to follow a chronological order similar to the finite element method series, and I will try my best to be able to implement something in robots, at least if I think that we can. And this course is following a book from Klaus-Jürgen Bathe called Finite Element Procedures. Now, this book is a nightmare to read. It's basically the grandfather of all the finite element method books, but it's kind of really strange to read. I recommend you read it once you hear my lecture, not vice versa, because I will try to simplify what is inside the book. We are gonna start with chapter 6, the finite element nonlinear analysis in solid and structural mechanics, because the first chapters before that are basically the finite element method that I explained to you in another video series. Daryl and Logan had a better job in explaining it simpler. With that being said, well, let's start with this, so sit back, relax, and enjoy the show. Now, although most of our calculation and designs based on that calculation are based on linear analysis, the failure of our structure occurs in nonlinear domain, especially in modern codes. Thus, nonlinear analysis is indeed important. So what are the skills I'm assuming you have right now? I'm assuming that you have a good understanding of the finite element method. If you don't have that, I will link my video series in the top right talking about the finite element method. Also, I'm expecting you to have a good knowledge in mechanics of materials, especially the stress-strain curves. If you forgot that, relax, I will try to mention those things again very quickly, but if you feel yourself lost sometimes, it's better to brush up very quickly on your mechanics of material topic. A good book I suggest to you is, there are two books actually, Mechanics of Material for Hibbler, and this is one of the famous books. Also, Ferdinand Beer and Johnston is the book I actually studied on. If you use Hibbler's book, you should read chapter 3, which talks about the stress-strain curves and the elastic modulus. So, of course, as I said before, in case you're missing any finite element knowledge, this is the video series I'm recommending to you. We have it on the channel, and I have linked it just now on the top right. So those are the things I'm expecting you to bring with when you come to this video series. Now, to mention, this is our first MSc level course. This is something that you would learn in the MSc level. This is interesting for individuals who are interested in structural engineering, for academic purposes and for practical purposes. Because, look, you have softwares, they do nonlinear analysis, but of course, we can't just use softwares as black boxes. You see that if you use softwares as black boxes, it's basically garbage in, garbage out. So we need to understand what those softwares magically do. Alright, so what is a linear analysis? A linear analysis is an analysis where everything has a linear relationship. meaning the relation between the inputs and the outputs is linear. F equals kx, meaning if you double the force, you double the displacement. And if you get half the displacement, you mean you have inputted half the force. Easy enough, I think that's understandable. In this course, before we start, we are going to be using Ku equals R. This is a slightly different notation from F equals Kx. F equals Kx is the notation I used in my finite element series because the book Daryl and Logan uses that notation. Also, it's kind of closer to the heart because F stands for force and X is usually positioning or displacement. Ku equals R is the notation that the book Klaus-Jürgen Bathe is using, and you can see that this is some kind of strange nomenclature, but it's an academic book, so we're going to use this for our displacement, so U is our displacement, and R is going to be our forces or moments. It might need like a video or two to get familiarized to, but I will be using this because the book equation is based on U and R, so I don't want to keep rewriting all the equations. K is your good old stiffness matrix, U is the U capital, my teaching assistant messed up, U capital is the displacement rotation vector, and R is the force moment vector. Fantastic. Why are we changing the symbols? Because Klaus-Jürgen Bathe's Finite Element Procedures uses those symbols, and we want to keep the same thing with him. Because you might want to read the reference, and if I use F equals Kx, and then you bump into R equals Ku, you will be confused. So I'm gonna unify my symbols with the symbols of my main reference. I think this makes sense, so I'm warranted to do that. We said that linear analysis is basically linear relationship between force and displacement. Double the force gets double the displacement. But is that actually true? Is the assumption of linear behavior actually true? Well, it is and it is not. It's an answer of yes and no. You see, it is true up to a certain limit, and then untrue after the certain limit. So what is this limit? Well, there are multiple limits here, but I want to mention material behavior as one of the limiting factors. For the geeks among you, you already know that there are two nonlinearities, a material level nonlinearity and a geometric level nonlinearity, but I want to mention material for now. Is the linear assumption true? It is true up to a certain limit. What is the limit? Well, it is based on the material behavior, that's one of two types, and because material behaves linearly up to a point, you can analyze linearly up to a point. After that, the material behaves nonlinearly, and then you should capture the nonlinearity by making a nonlinear analysis. You see, the stress-strain curve of metal kind of looks like this, with a well-defined linear domain, and that's where your knowledge and mechanics of material comes into play, a yielding point, a plastic region, a necking point, and a rupture point, all those cool, amazing points that you have in your typical stress-strain curve of a steel metal, for example. Now, because of that, you have a linear behavior up to the yielding point, and then you have a nonlinear behavior after that. As long as you are in this domain, if you double the load, you get double the displacement. But for example, here, if you double the load, you got much more displacement. So it's kind of a different thing. Also, this is called the bilinear idealization, where I idealize my curve into two curves or two lines, one line straight up, which is the linear domain, and one line to kind of approximate the nonlinear domain. In case you're wondering, why does the line look like this? Why not a little bit up? Why not a little bit down? This is based on curve fitting because we want to have the minimum error. So this red line is usually based on the least squares approximation or curve fitting, meaning that we try to keep the error below and the error above equal if you add them together. I know you mathematics geeks are now facepalming. I know that the reality of the matter is that I should minimize the square of the error, but I'm trying to use simple language. So for the mathematic geeks, yes, the least squares method is, as the name suggests, the minimization of the square of the error. Anyway, let's dive into this. So because of our material nonlinearity, our linear behavior is kind of untrue and true. It's true up to this point and untrue after it. Now, there is another thing. You also have other reasons why linear is incorrect. For example, you have geometrical considerations. You have large displacements and even buckling, because buckling does matter. For a column, you have a linear behavior between the force and the displacement. Delta equals PL over AE. This is from mechanics of materials. P is the axial force, L is the length, A is the cross-section of the column, and E is the elastic modulus. And this relationship is linear, because if you double the P, you get double the delta. This is true up to a point when it starts to buckle. When the column starts to buckle, you will realize that there is a certain failure or loss of stiffness that happens here. Basically, when the buckling starts, then suddenly doubling the force could even lead to the failure of the structure. So this is nonlinear, and this needs to be taken into account. Buckling is one of those nightmarish problems that you can be faced with, and that's why design codes, actually try to avoid or approximate this by doing some KLU over R shenanigans. So you might have seen this before in your design codes. KLU over R is kind of a controlling factor for buckling, and you will see that codes actually tell you that it should be above a certain limit, otherwise you would have to deal with buckling. Also, there is large displacements, although not shown here, and there is even nonlinearity due to geometry itself, due to structural geometry. For example, if you have a von Mises truss, it's a very well-known problem in engineering. If you have a von Mises truss and you apply a vertical load on it, it will resist the vertical load up to a limit, and then suddenly it snaps and flips back on the bottom side. Kind of if you hold a playing card, you know the playing cards, like the Jack of Spades, for example, those playing cards. If you hold them between your fingers, like you have a finger here in your hand and a finger here. I know my hand kind of doesn't look like a hand. It looks like a Lego hand. If you hold the card like this and buckle it between your hands, between your fingers, and then you push with another hand the card down, it will snap and it will flip on the opposite side at a certain limit. This snapping action is called snapping through, and this is something that is nonlinear in behavior. And of course, the von Mises truss or shallow structures in general do have this behavior. So why would I even consider nonlinear analysis besides the benefits of understanding it? Well, because economically you can tap into material reserves. Like when you deal with linear domain, you are actually limiting yourself and you're not tapping into material reserves. You can only access material reserves if you apply nonlinear theory, such as plastic hinges and moment of distribution. It's basically Kaioken. I don't know what this word means. My teaching assistant kind of insisted on me mentioning this. So it's a kind of Kaioken times 3 thing that you do on your structure when you do a nonlinear analysis. This is kind of a high risk, high reward thing, similar to what the Kaioken is. Again, that's something that my teaching assistant told me to say, because it seems that you are accessing or tapping into reserves, but of course, since you are tapping into reserves, the reserves are no longer available for you, and this means that you need to be very careful when you design. You kind of can get away with some approximations you do in the linear domain, because look, when you analyze linearly, you kind of get away with some approximations you're doing, because you always have this get out of jail free card by saying that, you see, I'm doing linear analysis, although the reality is nonlinear, so we have reserves. But if you now consider nonlinear analysis, then yes, you can have smaller sized sections, but then you don't have the material reserves. My personal point of view on this thing is that nonlinear is actually the more accurate analysis of linear. So I am a fan of nonlinear analysis if it is a thing that warrants it or has cost savings. And sometimes there is only nonlinear analysis I can do. For example, if I have a von Mises truss or a very shallow roof, then I would only analyze nonlinearly. I would not even touch linear analysis in that case. But that's something that I might explain to you later. It's not only about economy, it's also about safety because of buckling and von Mises trusses. So yeah, that's basically why I would consider nonlinear sometimes. Feel free to tell me other scenarios in the comment section. I am always reading your comments and trying to reply to them, maximum 2 days. So yeah, feel free to discuss this in the comment section. What are the assumptions that are included in linear analysis? Because if you understand the assumptions of the linear analysis, then you can understand what the nonlinear analysis is. Well, first of all, the first assumption in the linear analysis is in its name. It's a linear analysis because there is a linear load to displacement relationship. F equals Kx or R equals Ku from now on. This is a linear relationship. Double the force, you get double the displacement. The other assumption that is inside it is that strain is below the yield strain, and even if it is exceeded, we are still using the linear elastic modulus, meaning we are still dealing with material linearity. This is one of the approximations that is in the linear analysis, because we know that our material might be yielding and it might not be linear at all, and we are still using the linear elastic modulus. This is one of those approximations we are dealing with when we analyze linearly. We also mentioned that displacements are small. If they are large, then there are a lot of approximations that we cannot use because we are using engineering strain. Also, if the displacement is large, then you can have some sudden non-linear behavior like snap through in a von Mises truss. Something I did not mention before is the nature of boundary conditions. A pin is always a pin in linear analysis. Even if I apply an infinite amount of load, the pin will be always able to support it. Fixed support is the same here. However, that is not true because there are conditions where the support fails. Because look, when I put a beam like this and I put a pin here and a ruler, well, that's a bloody lie because the pin is actually a column carrying the beam and the ruler is actually a column carrying the beam. And this column doesn't have an infinite stiffness. This column has a stiffness, and even the column itself is nonlinear, so if you apply extra loads, you might get nonlinear behavior from the support. All of this is not included in the linear analysis. The support can carry any force you need it to carry. The support basically never fails. If any of those assumptions is not fulfilled, then the analysis becomes nonlinear. So one final thing I want to mention in my introductory lecture is the classification of nonlinear analyses. The classification of nonlinear analysis is well, first of all, this is taken from Klaus-Jürgen Bathe's book. So please notice that anything that is taken like a scan, the reference is always going to be Klaus-Jürgen Bathe. I want to mention this because, I'm an academic and I like to reference stuff I put here. If it's not something of my own production, then I need to reference it. Now, there are a lot of things and a lot of gibberish you will see here. Relax, I will explain this to you later. Material nonlinearity only, this is the easiest nonlinearity you will be faced with. And there is description, typical formulation, and stress-strain measurements. You also have large displacements, but small strain, and you have large displacements and large strains. Those are kind of gibberish, but I will explain them to you later. For now, I want you just to realize that there are some nonlinearity types. You can also have a mixture between material and geometry. You cannot have a mixture of those two things because those two things are mutually exclusive. You cannot have small strains and large strains, but you can have material nonlinearity with large displacement, small strain, and material nonlinearity with large displacement and large strain. And the formulation is, well, there's like some gibberish here. Total Lagrangian, updated Lagrangian, and second Piola-Kirchhoff stress, Green stress, Cauchy stress, Almanzi stress. It's really a lot of words here. And so far, you might think this is Chinese, and you are right. You are right in this because, trust me, when I studied this, it was for me like, what is this even talking about? And is there something that is not an engineering strain? Was everything I studied so far a lie? Or is this the truth? Well, I will tell you all about this in the future videos. So for now, I just want to mention that those are the types of nonlinearities you have. We will revisit this later once we establish some of those definitions. What are those definitions? What's the meaning of this? Now, please notice that the book will go full on mathematics here and start talking about tensors and whatnot. I'll try my best to avoid talking about tensors. If you are an MSc or PhD student, you immediately know that tensors is one of your worst nightmares. If you are not, you can just Google and see what tensors are. Tensors are the nightmare brother of matrices. But of course, you are here in the Civil Engineering Essentials channel, and we will try to keep it simple and keep it understandable. This is gibberish, but we'll explain this later. So yeah, that's as usual everything I wanted to talk about today in my introductory lecture. I hope you enjoyed it. And before I finish, I want to give a huge, non-linear sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. Trust me, their contribution to the channel is really priceless to me and enables me to provide you with the videos I can no longer say on time, but with a certain quality I try to achieve, and for that I am forever thankful. Of course, I hope that you enjoyed the video and that you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing as a sacrifice to the YouTube algorithm overlords. With that being said, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.